In this video, I want to talk about one of the homework problems that apparently caused a lot of difficulty on the last homework assignment, and it had to do with the homework problem that went like this. If you take a divided by the GCD of a and b, take b divided by the GCD of a and b, and then take the GCD of that, then the GCD of those two quotients is actually equal to 1, so that these two numbers here, a over GCD AB and b over GCD AB, are actually relatively prime. The idea of the proof is fairly straightforward. The idea of the proof is pretty straightforward, and it makes common sense. If a is equal to 12 and b is equal to 20, then there's 12 is equal to 4 times 3, and 20 is equal to 4 times 5, so that the greatest common divisor is equal to 4, and there's no other common divisor besides 4 that's larger. So if I take 12 divided by 4, that's equal to 3, and 20 divided by 4 is equal to 5. And if I take the GCD of these two quotients, 3 and 5, that's 1. Those 3 and 5 are relatively prime. So that's the theorem that we wish to prove, that if I divide two numbers by their greatest common divisor, then the quotients that are left have GCD of 1. Okay, now why is this true? So let's prove it. Let's first suppose that D divides the first term, a over GCD AB, and suppose also that D divides the second term, b over GCD of a and b, where D is a positive divisor. I need to show that the only way that's possible is if D is equal to 1. Okay, to do so, let's look at the definition. If D divides this number, then that means that number is equal to D times J for some integer J. Likewise, if D divides this other number, that means this other number is equal to D times K for some integer K. So let's take these equations and write them in terms of a and b separately. So clearing out the denominators, that means that a is equal to j times d times the GCD of a and b, and likewise b is equal to k times d times the GCD of a and b. Now notice that means that d times GCD of a and b is a divisor of a, and also d times GCD of a and b is a divisor of b. So that means that D times GCD of a and b is a common factor of a and b. It is a common factor of those two things. Well, that's kind of funny because GCD of a and b is supposed to be the greatest common factor of a and b. So this is a common factor. This is supposed to be the greatest common divisor. And therefore, the only way that happens is if D times GCD of a and b, this common factor, is less than or equal to the greatest common divisor, a of a and b. Well, the greatest common divisor is positive, so I can divide out, and so that means that D is less than or equal to 1. Well, by assumption, of course, D is a positive integer, and so if D is less than or equal to 1, and D is a positive integer, the only way that can happen if D is equal to 1. So in other words, if D is a positive common divisor of these two quotients, a over GCD of a and b, and b over GCD of a and b, then D is equal to 1. That is the if there's a common divisor, then that common divisor is equal to 1. So the only common divisor of those two fractions is 1, and therefore the greatest common divisor of those two quotients, a over GCD a and b, and b over GCD a and b, is equal to 1.